Hi, my name is Maria, and in this video I'll be introducing you to an online model fitting platform called fitteia. There is such a huge variety of model fitting softwares nowadays that you are probably wondering if there is really an advantage in choosing fitteia. Well, being an online platform, fitteia enables you to quickly and effectively perform basic to advanced model fitting anywhere you are using either your cell phone, your tablet, or your computer, and without having to worry about common software incompatibilities. There is only one requirement, and that is proper internet access. In this tutorial, I will explain how you can create an account and use fitteia to perform a basic linear fit while covering most of the visual aspects of the interface. Let's start. If you access fitteia.org, you can find a list of functionalities as well as several links to the existing servers. It does not matter which one you choose because they perform periodical mutual backups in order to secure the user's accounts in the event of a malfunction. I'm going to choose the first one. Let us then create an account. For this, you only need a valid email. I will start by clicking on Sign Up. Then I should write my email, which I have created specially for this tutorial, and click on the Sign Up button. To prove that I am human, I simply have to type in the 4 digits that are presented to me and click on Email Password. Now I am presented with this form, which I have to fill in with a name. Basically, you can write anything here. Let us put banana. The old password should have been emailed to me, so I just have to copy it from my email account that I have provided. Choose a new password, ideally something that I can remember more easily than the email password. Confirm it and press Finish. You can also follow this procedure if you already have an account and wish to change your password. Now I can click on Login. And this is what fitteia looks like in your first access. It has this Tutorial 1 folder, which we are going to open in order to perform a basic linear fit, and the Tutorial NMR folder, which was created specifically to solve nuclear magnetic resonance-based problems. So if NMR is not your area of expertise, I suggest that you just ignore this folder, at least for now. There are 3 main areas that can be distinguished now. The first one is this big white rectangle where you are supposed to input your data divided into 3 columns. The first column is for the independent variable x, the second column is for the dependent variable y, and the third column is for the uncertainty of the dependent variable EY. We can see that there are already some sample data here, which we can plot by clicking on the Data Plot button. When we do this, we reveal the graphical representation of the data. In this first area, it is also possible to neglect some of the experimental points by starting the corresponding line with a hash and to perform algebraic operations in any of these elements. For example, I can comment the second point and multiply the uncertainty of the last point by 2. When I click on Data Plot again, I see that the second point was not considered in my representation and that the last one has a doubled uncertainty. The second main area of the interface is where I can control the visual aspects of my representation. I can define the axis labels, the maximum and minimum values of the scale, its increment, the title of the graph, and so on. Finally, the third main area is where I should write my model, which is conveniently set as default to a straight line equation. The model should be written in C language, but you can see that in this case, C basically reduces to normal algebraic language. As an example for this linear fit, I am going to use the damped oscillations of a pendulum. It is generally intuitive for a person who has observed pendular motion, you can imagine a swing, for example, that as a result of friction, the maximum angular amplitude of the oscillations will decrease with time until it becomes 0 when the pendulum eventually stops. Naturally, taking a swing as an example, I am also assuming that no one is pushing the swing, or to say it in another way, that its oscillations are not being forced. As it turns out, for small angular displacements, this decay is exponential, has a characteristic damping coefficient L, and an initial angular amplitude A0, which means that we can apply the natural logarithm on both sides of the equation in order to linearize our problem. Maybe we can change the name of the variables here in this model so that they convey a little bit more meaning regarding our problem. So our independent variable is the time. Let us change this to t. The dependent variable is the natural logarithm of the maximum amplitude. So we can probably write log of a here instead of y. A can be replaced by the logarithm of the initial amplitude, so log a0, and b will be the damping coefficient L. Now we can click Compile in order to verify that everything was properly written. If we come back down to the model area, we can read here the message compiled without errors, which basically tells us that everything's okay. Now for the experimental data. There is a tool called Tracker that allowed me to analyze the video of the pendulum that I have shown you previously. With the tracker, I can follow a chosen mass point and obtain its coordinates variation with time. In this case, I acquired the angular displacement, and I can paste the data from the table directly in the big white box. This first column is the time in seconds. The second column is the angular amplitude in degrees, which raises a problem because what I really want is the logarithm of these values. There is also another problem, since I need the third column with an uncertainty of the maximum amplitude, or in this case, of its natural logarithm. You can see a smaller area here below the data, which is a calculator. This is very convenient to solve the problems that I have now, because it allows me to perform mathematical operations on my data columns. So what I need to do here is to keep the first column, C1, and the second column. Let us first solve the uncertainty problem. And let's say the error associated with the angular amplitude measurement is fixed and around 0.1 degrees. So I type in 0.1 for the third column. If I now press Calculate, you can see that the uncertainty column was properly generated. Now I need to keep the first column to calculate the natural logarithm of the second and its error. As you may imagine, if I take the logarithm of the second column, the numbers I will obtain will be much smaller than the ones written here, so the error should also have some kind of treatment. There is a rigorous way of making error analysis and propagation, which is a very important topic if you want to do proper model fitting. But in the interest of keeping this problem simple, I will just say that the uncertainty of the logarithm is given by the following equation, related with the representation of the logarithmic function, and direct you to a future video we shall make on this topic. Then we should write on the calculator C1 log C2, which is the natural logarithmic function, and 1/2 times the logarithm of the maximum amplitude plus the uncertainty minus the logarithm of the maximum amplitude minus the uncertainty. If we leave the first line here, then fitteia will perform this calculation again. In this case, it's okay because this would simply return the data that we already have in the box. But if you wish to neglect these calculations, it is possible to comment them with a hash. Press Calculate, and 3 columns were again properly generated. If I now plot this data, I will see nothing, because the scale set as default does not allow me to. I can use the auto-scale options by choosing Yes on the drop-down list and replot the data. Maybe I can also refine a bit the settings generated by the auto-scale until I obtain the representation that I want. In the x-axis label, I can write time in seconds. And for the y-axis, I can write maximum angular amplitude log. Let us set a minimum of 15, a maximum of 35, an increment of 5, 0 precision for the x-axis, a minimum of 1, a maximum of 3, and an increment of 0.5 for the y-axis. Let us also decrease the symbol size to 0.5 and set the title to Oscillation Amplitude Damping at x equal 18 and y equal 3.2. These are the coordinates of your title. Data plot. I think this representation looks very reasonable now. We are now in condition of performing the actual fit. We can see that our parameters are set as default to 1 and that they are both fixed. If I want to fit the model to my data, at least some of my parameters should be free so that their value can be optimized. I am going to free both my parameters and click on the button Fit. I have successfully fitted a straight line to my data, and with that I have determined, based on this data, the damping coefficient. The program uses a least square minimization method, which consists of the minimization of this value here, the chi-square. This is the sum of the square difference between the experimental value and the theoretical value divided by the uncertainty. You now see the importance of your uncertainty. If it is not constant for all the data points, it means that the fit is going to be better where the uncertainty is smaller than when it's larger. If you wish to disregard the errors, you can simply choose an uncertainty equal to 1. Let me show you also the function of the plot button. If I change the parameter L to 0.06 and plot, fitteia will simply draw a straight line with the parameters that are given here. No fitting is performed. The exact same thing happens if I fix all my parameters and click Fit. A plot is then a fit with all parameters fixed. It can be helpful, for example, if you want to understand the effect of a parameter or of a combination of parameters on your fit. You are also able to set minimum and maximum limits for your parameters, remembering that you cannot set a minimum and not set a maximum. You have to set them both. I can write here that my parameter L has to be between 0.06 and 0.08 and fit. You see that the damping coefficient wants to be even larger. I can then increase the limit and obtain the right value. Before saving this fit, I would like to make one last thing. Suppose that you are absolutely sure that the initial amplitude logarithm should be 3.9. You can force this value by fixing it. If you do so and click on Fit, the damping coefficient is optimized in order to accommodate the forced value of the other parameter. As you can see, this software allows for a complete control over your graphical representation, data, parameters, and overall fit. We are now in condition of saving this. Simply go to the top of the page, choose the name of the folder you want to save the file in, and the name you want to give to the file. Let's create a folder called Tests, and call this file Pendulum Damping. You have two options now, either overwrite, which creates a file with the name but no date and time associated. So every time that you save a file in the same folder and with the same name, it will overwrite the already existing file. Or archive, which will associate a date and a time to the name, preventing you from ever writing over this project. If you click on My Fits, you will see that in addition to the two previously existing folders, there will be a new folder called Tests, which contains the saved projects that you can recover anytime. Now, finally, and to prevent other users from getting into your account, do not forget to log out. And that's it! Thank you for watching. We have learned how to create an account on fitteia and used it to perform a basic linear fit. But I assure you there is still a lot more to learn. I hope you found this video helpful. Either way, enjoy fitteia and I will see you in the next video. Bye!